These are examples for lesson 1-1, points, lines, and planes. In this video, you'll visualize several different combinations of points, lines, and planes and determine how they relate to each other. You'll also identify various geometric terms that are defined and undefined. And finally, you'll learn how to use geometric language to write statements that communicate geometric situations. Example 1. Here we have a plane. Remember, a plane goes off in all its directions. It's flat, 2D, two-dimensional. And even though this looks like a parallelogram, what it really is a plane that's being kind of bent backwards in space. We also have two lines. One is going through the plane at point Q. Another line is in the plane, in this plane right here. This line and this line, so there's two lines, and then there's one point apart from both of those lines. It's also in the plane, point V here. Part A. What are two other ways to name line QT? So locate or identify line QT. It's the line that goes through T and Q. It continues upward and it continues downward. And of course it goes through point N here. They want two other names for line QT. So as long as we have 2 points on the line, then we can name that line in a different way. We could also name a line by a lowercase letter. In this case, they've given us lowercase m. So I'm going to start with that one. So this is line M, lowercase m. And another way we can name it, I'm going to use point N since it's on the line, and I'm going to use point T. So line NT. So you write both the points, both the points on the line, and then you draw a line over it. Remember, arrows need to be on both sides of that line. These are two different ways to state line QT. Now there's some other ways to do it. We could have named it TQ, line TQ. We could have named it line NQ, or we could have named it line QN. As long as there's 2 points on the line being named, uppercase letters are points or represent points. So this is our answer. These are other possible combinations of answers. Part B. What are two other ways to name plane P? Plane P is the only plane pictured here. That doesn't mean there are not other planes in the space. It's just that it's the only plane that's drawn or pictured. Plane P. One other way we can name planes is by using at least 3 non-collinear points. That means 3 points in the plane that don't line up. So, for instance, we could not use points R, Q, and S to name this plane because they're all in a line, or they're collinear. As long as they're non-collinear, we can use them as long as they're in the plane. So, for instance, we can call this plane P. We can call it by using 3 points, point R, Q, and V. Plane RQV or plane QRV or plane VQR, it doesn't matter the order. But one thing you need to make sure of is that there are no commas between the letters. If you put commas between the letters, you're no longer naming a plane, you're naming 3 separate points. So be careful with that. Commas or lack of commas are important. Another way we could name this plane is by using another combination of 3 non-collinear points. How about S, R, and V? SRV, plane SRV, or VRS, or RVS. Now there is another way to name it, but they just asked for 2. Another way we could name this plane is points VQS, or VQS. Part C. What are the names of 3 collinear points? And there's a second part to this. What are the names of 4 coplanar points? So starting with the first part, in part C, what are the names of 3 collinear points? Collinear means all in one line, And so as long as you have 3 that line up in this illustration here, you've got 3 collinear points. And we're going to separate them with commas so that they're distinct, 3 distinct points. One combination of 3 points that are collinear would be points N, Q, and T. They're all in a line, or they're collinear. So point N, point Q, and point T. These are all collinear points. Another possibility is you could have used points S, Q, and R with commas between them, and those are 3 collinear points. The second part of part C asked us for us to name 4 coplanar points. When you name coplanar points, as long as all the points they're asking for are not all in one line, you've got, and they're all in the plane of course, you've got coplanar points. For instance, points R, Q, S, and V are all coplanar. So for our coplanar points, this was collinear. For our coplanar points, points R, Q, S, and V. V is vital for our listing because if we only named R, Q, and S, those are collinear. So this point V allows us to name all 4 of these as coplanar. Example 2. This example helps us practice writing names of geometric elements in different ways, and we're going to introduce the ray here. When you talk about rays, things get a little bit more complex. Part A. What are the names of the segments at the right? So starting with segments. Remember, a segment is part of a line and it has 2 endpoints, one on one side, one on the other. So for instance, we have segment, line segment, DF or FD. And by the way, segment DF and segment FD they're exactly the same thing, whether you're naming them in one direction or the other. So if they're asking for you to name one segment, you don't use both of these, you only use one of them. That's not going to be true of the ray, but for the segment it is. So we have segment DF, that's the segment right here from here to here. Then another segment that's not the same length would be segment DE. It's a shorter segment, so we have DE or ED. And then finally there's a third segment, segment EF, apart from the other 2, or FE. So those are the segments in this picture. Part B. What are the names of the rays in the figure? Now, when you first look at this one, you think, well, this one's not going to take very long. It might take about as long as this one did. But if you look a little closer, it can be a little bit more difficult. So what we're going to do is we're going to take a straight edge, and we're going to keep track of the rays that we start naming so that you can see something that is going to pop up here in just a second. Remember, a ray starts at a point and continues on in another or the opposite direction forever. So, let's start with point D here. And I will trace ray DF, or not trace it, but we'll copy ray DF out to the side parallel to this one. There's F. So ray DF is one of the rays. It starts right here and goes off forever that way. So ray DF is one of the rays. Notice we start with the end point and we move over to the point that continues on forever. So the end point is on the left, D, not the F. Next, what about ray DE? It's got one of the letters is different, but look what happens when we draw it. Here's D, and there's E. And when we start at point D and we draw that way, look at that, we get exactly the same ray. So whether we call this ray DF or ray DE, it's naming exactly the same ray. So therefore, either we would write ray DF or we would write ray DE, but not both. So that one we're not going to use because we've already used this one. Now, if we start at point E as our endpoint, that's not going to be the same ray as when we started at point D. So I'm going to draw ray EF. And that's a brand new ray. Starts here and goes off this direction forever. So ray EF is another one. Starts with E, endpoint is E, and the arrow goes to the right, always to the right. Then, starting at F, we have no points identified after F, so we can't start with F and go that direction. But we can start with F and go back this direction. So let's look at ray FD and copy it over here. There's point F, there's point D. Ray FD. That's a new ray. And notice it's not the same as ray DF. DF starts here and goes on that way forever. Ray FD starts here in a different location, goes that way forever. So that's a different ray. And so we come over here and we think, well, what if we started with point F again, and this time we said ray FE. Well, ray FE, even though the D is no longer there and the E is, F is still in the same location, it's going the same direction. Therefore, these are exactly the same ray, and we could erase this and write ray FE, or we could just leave FD, but not both. And then finally, if we start at point E and go this direction, we have ray ED. There's E going this way. So ray ED would be our final and fourth ray. The order of rays being named is extremely important. It's a lot more complex than just doing segments or lines. Part C. Which of the rays in part B are opposite rays? Recall that opposite rays share the same endpoint, but go off into opposite directions. So opposite rays. Well, F is not common to both for two rays here. We've got one going off this direction, and going off this direction there's no point to name. And the same with D. The only point we can use as a common endpoint for opposite rays in this particular picture is point E. So ray EF, this one right here, and ray ED going off in the opposite direction. It has to be the opposite direction, and so that's ray ED. These are opposite rays together. They're one thing. A pair of opposite rays are these two. That's the only possible combination of opposite rays on this example. Example 3. Now, before we do this problem, I want you to notice that this is a solid represented on a flat sheet of paper. And when that happens, when you're trying to represent something in 3D, three-dimensional solid, on a 2D flat sheet of paper or surface, you have to remember some things. We must remember that when two planes intersect, that they always intersect in a line, not a line segment, because remember, a plane goes on forever in all directions. So if two planes intersect and they both go off in all directions, then the line that they intersect at is going to go on in both directions. I'll show you a little bit more about that here in just a minute when we do this problem. Not a line segment, but a line. Also, again with the three-dimensional figure, we've got to see that this is the top, this is the bottom, this is the left plane, this is the right plane, and this is the back plane here, and this is the front plane. So, with that said, the problem asks, each surface of the box at the right represents part of a plane. What is the intersection of plane ADC and plane BFG? So, when you get a problem like this, where there's two or more planes, what you want to do is take the first plane, take all the points on the plane named, and identify them some way on the picture. I'm going to use a circle on this first one. So point A, in this plane, point A, point D, so locate D and circle it, and point C. And then at that point, you'll notice that all three of these points, here, here, and here, if you were to connect them into like a triangle, notice that if this continued this way, it would also cover point B, right here. So the plane ADC, if you'll shade it in, it'll help us identify the intersection when we get to the other plane. So let's go ahead and shade in this top plane because it's plane ADC. It includes point B. They just happen not to use point B in the name. The next plane BFG, do the same thing except mark them a little bit differently. I'm going to use points, darken in the points of these. So B, F. Now so far we could either be talking about this plane or that plane. But then have G here. So plane BFG is the plane that is on the right side of the box or the prism here, like this. So you have a plane going vertically and you have a plane going horizontally, and they intersect, or they meet where? They meet right here. And before we say line segment, remember these planes go off in all directions forever and ever. So really they meet at line BC or CB. So the intersection of these two planes is at line BC or CB, line CB. Example 4. From your list that we went over in our notes of basic postulates, there should be about 10 of them, 7 to 10. The plane postulate states that through any three non-collinear points exists exactly one plane. Once again, the plane postulate says that through any three non-collinear points, these are non-collinear, exists exactly one plane. This plane right here. Using that theorem, the concept behind it, take a look at example 4 here. Use the plane postulate, one we just talked about, with each figure at the right. A. What plane contains points in, that point right there, P and Q. So can you identify which plane that is by shading it? That's right, it's the bottom plane. So I'm going to shade the bottom plane. It also includes which point? Point R, right over here. And so we shaded the plane, and there's our answer. It's pretty simple. Part B. What plane contains points J, M, and Q? And they want us to shade it. J, M, and Q. Uh-oh, that's a little different. J, M, if they had said L with M and J, that would be easy. That would be this top one. If they'd have said J, M, and R, that would be easy. That would be the one on the left. But they're saying Q, and they're leaving out K, L, and P. So what in the world are they talking about? When you get one like this, it's a little harder to see. go ahead and lightly connect the 3 points they give you. Use a triangle. And notice that's part of a plane, this triangle right here. You notice which direction it's going. It's kind of a diagonal. It's running diagonally through this box. It goes through these two, and it goes through Q, but it also goes through point P right here. So the plane that we're talking about is the plane that contains points J, M, Q, and P. So here it is again. Now the triangle you drew, this diagonal in the triangle, or the diagonal, you can erase it now or you can keep it there. And this is the plane that they're referring to. The plane actually was not drawn on our diagram. We had to draw the plane. There's your answer.